I will begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for students. And I just pray you bless our work this day, Lord. In your name I pray. Amen. All right, so I wanted to go through the corrections to this PDF with you guys. And so the point of doing this Smith normal form calculation on a matrix is, the point of it is that it reveals the list of invariant divisors. All right. So we know some things from the general theory. For example, the product of the invariant divisors should be the characteristic polynomial here. I guess that's not the general theory. That's the theory particular to the fx module built over, the linear transformation induced by A. I mean, basically we're looking at T L sub A, if you want to make the connection to the V upper T. Here V is equal to R3 or Q3. Pick your favorite field, which makes sense of this calculation. It's C3, I don't know. But any fields you like that include 0, 3, and 6, so you got lots of choices. But in any event, this first example still made sense. It made sense the first time, it makes sense now. It's because this is diagonalizable matrix, and that's its minimal polynomial, right? Which is also its characteristic polynomial in this case. This matrix is said to be non-derogatory. All right. Example 2 was also cool. Example 3 was fine. Again, in each one of these, you're looking at the, it's kind of boring in some sense, the minimal polynomial here, that was diagonalizable. This is the minimal polynomial. As you can see, it's not a product of linear factors, not repeated, reflecting the fact that this is not diagonalizable. In fact, this is the quintessential Jordan 2 block with eigenvalue 3. This is the real Jordan form with eigenvalue I. You may or may not remember, but no accident, we get characteristic polynomial x squared plus 1. Well, that's also the minimal polynomial. And by the way, so this is interesting. If we were to do this calculation over the complex numbers, we could factor this into x plus I times x minus I. And then you'd see that it is complex diagonalizable. And yet it's not real diagonalizable or rational diagonalizable because, of course, you can't factor x squared plus 1 over the reals or rationals. All right. All right. Not telling you anything terribly surprising here. This one, I stopped short. And not like in Seinfeld. Let's see here. Sorry. Where was I? So I think I got to like, where was it? Wait, I can't remember where I got to. Maybe here. And then I was like, okay. I didn't know where to go from there. But the thing is, this is definitely not in Smith normal form, because Smith normal form should have the list of invariant divisors with the divisibility conditions stacked up on the diagonal. All right, and of course, x minus 2 does not divide x minus 3. These are distinct primes in the polynomials. So, in fact, they're relatively prime, and here's how to build the unity from them. So that's basically what you have to look for, is how you can build one from a linear combination of the factors that you're facing. If you can see what that is, then you know how to do the column and row operations to make the thing go away. All right, so once I had this in mind, then I was like, oh, okay, so I need to make a copy of this come up here. So a way to do that was I took row 3 and added it to row 2. Okay, actually, no, I took row 3 and I subtracted it from row 2, because I knew then I could add columns to column 3 to column 2, like that, and then the x minus 2 plus minus x plus 3 just gives me 1. Once I have that 1 there, I can clear out below it, which is the interesting thing I should do first. Clear out below it, and that will end up putting as it happens, x minus 2 times x minus 3 in this spot, because I have x minus 3 minus x minus 3 times 3 minus x. And that works out to this product right here. I'm not sure where I put the work on that, but it is true that, again, x minus 3 minus 3 minus x times x minus 3. That gives you x squared. Well, I may not say it out loud. It works out to this, though. And then you can, once you've done that, you can clear out, use the column operations to take that pivoting 1 and clear these out. All right, and if you've already cleared out below the 1, clearing out to the right of the 1 doesn't cost you anything, because you can just take multiples of this and clear out whatever's over here, which would happen to just be 3 minus x. And so that leaves me this, at which point I'm done. Because when you look at this junk down here, you take the greatest common divisor of all these guys, and you're just looking at the non-zero ones. X minus 2 and x minus 3, yeah. So the greatest common divisor of these two things is either, it's just, there it is. And so that's the Smith normal form.
So anytime you get to a diagonal matrix where you have the divisibility down the diagonal, that will be unique?
That will be unique up to associates, yeah. But yeah, that's the Smith normal form. So the larger point here is we can do Smith normal form, provided we're doing what? We're working, we need the, you can start to see here, what sets this up? Certainly we can do this over the integers, because we have, what is it, Bezow, whatever. Yeah, Bezow. And so anytime we have a division algorithm, right, so we actually need like a Euclidean ring to do the Smith normal form. All right, so it's not an entirely general calculation. We do need some divisibility to play with. Oh, but getting back to the point here, you can see that this originally was, of course, a diagonalizable matrix, right? We still had minimal polynomial was x minus 2 times x minus 3. And if you think about it, you could have written down the Smith normal form looking at this alone. Because if you think about it, you have to have minimal polynomial x minus 2 times x minus 3. Then you have to have something else above it that divides the last thing, which is the minimal polynomial, right? But what else do you need? You need a product of invariant factors, which is quartic. You cannot afford to append just x minus 2 or x minus 3, otherwise you face my wrong answer, which doesn't have the divisibility condition. So it forces you to append next factor up, x minus 2 times x minus 3. That's the only thing you could put there in order to get quartic and the divisibility, if you think about it. Because the only kinds of factors you're allowed to put there are the ones you've already found in the minimal polynomial, right? Because the minimal polynomial and the characteristic polynomials share the same zeros. So if you're working over something where you have like an x squared plus 1, you should remember, well, you still have shared zeros, because you can always look at the complexification of your example. So you still have the shared zeros. Now, I guess this gets fussier with the rationals. But, well, no. We can always look at the algebraic closure of the field too, yeah. But be careful. As you know, you can't factor everything like you want to everywhere. All right, so you might or may not recognize this. This is basically the complex eigenvalue 3 plus or minus 2i with algebraic multiplicity 2, but geometric multiplicity 1. So this gives me the real Jordan form, like so. That's what you get from stringing out the real and imaginary parts of the complex eigenvector and complex generalized eigenvector in the real imaginary basis. Of course, I derive this in a stupid amount of detail in linear, but there it is. So if you do, I can forecast what's going to happen. All right? The minimal polynomial has to be quartic. So it's going to be x minus 2 plus 9, x minus 2 squared plus 9, parentheses squared. That should be the minimal polynomial. And then I think that's it. I could have written down the
x squared plus 5.
curses. Oh, see, this doesn't make sense, does it? I say fixed, but is it fixed? It's not fixed.
Well, right there you have it worked out, and it's the same thing. X minus 2 squared plus 9.
Oh, yes. That is not wrong. What is wrong is this correction I made here. This dot, dot, dot does not lead to this. This is impossible. This is impossible. Why? Because if that was the correct thing, you would have a list of invariant factors, which is quartic. Quartic. This is a 4 by 4 matrix. Does it have an 8th order characteristic polynomial? It does not. So let us fix the fixing. That should be 1. All right. So I was letting my logic for the case where the eigenvalues are in the field bleed over to this, which I shouldn't. Let's see here. If we were in the complexes instead of the reals, so keep in mind that's 1. Would it work out differently? What if we were working over the complex field? What would the Smith normal form be? Be the same? Yes. That makes sense, actually. Because, and just to be explicit about it, so you've got what? 2, was it minus 3? No, minus 3. 2. So, like I said, this is eigenvalue 2 plus or minus 3i, right? Twice. And so the Jordan form over the complex numbers would be and so if you look at that, it's pretty obvious that this, if you look at, j minus 2 plus 3i times I, you get whereas if you look at j so when you multiply these blocks, you don't get 0 because you get star times that nilpotent 2 by 2, right? But if you square these blocks, you square both of these blocks to get 0 in the upper or the lower diagonal block. So then when you take the product of the squares of these blocks, right? This is the smallest what do you want to say here? Expression that gives you 0 when you look at minimal polynomial. Well, m of j, let's say here, or m of x. Well, it's really x minus 2 squared plus 9 squared. But I've rearranged the complex factors. So what I'm trying to say is, you're right. If we just put this to 1 and factor that over the complexes, then you can see, yeah.
And that's because none of the steps are prevented by marking the field, right?
Right. Which is part of the reason this is leading us to the so-called rational canonical form, right? Why is it called rational canonical form? In part because it's determined by your rational base field. This one was kind of unenlightening, and yet it is also enlightening because it again illustrates the pattern which I was talking about, It's 2 by 2. It has to have a quadratic characteristic, but it's diagonalizable, which means the minimum polynomial has one of each eigenvalue. There's only one eigenvalue, 3, but it's repeated, which means we have to have this, if you think about it. Or you could just look at it and go, okay, well, if I look at the greatest common divisor of x minus 3 and x minus 3, I've got x minus 3, so I'm done. But, yeah. Example 8 was correct. All right, yay. And, again, this is the minimal polynomial. And you can see that if you actually try that out, plug in a into the polynomial, a minus 8i cubed. Well, a minus 8i is 0, 1, 0, 0, 0, 1, 0, 0, 0, and that's the nilpotent matrix of order 3. Its square is not 0, but its cube is. Yeah. And again, the product of the invariant factors is the characteristic polynomial. All right, here's another example. See if I had... Well, I wonder about this one now. Oh, no, it's good, it's good. The difference between this and the one I was just talking about a long time and on the board is what? What's the difference between this example and that example? I mean, they're both involving 2 Jordan blocks of order 2, but the difference with this one is that these are Jordan blocks with distinct eigenvalues, 2 plus 3i, 2 minus 3i, whereas this is 2 Jordan 3 blocks, right? And that leads us finally, after a while, to the minimal polynomial being x minus 3, and then we're forced to either, I mean, you could think about, above that, you could do what? You could have, I guess in principle, you could have what? You could have x minus 3, x minus 3. I mean, there really are 2 choices here. So knowing that the minimal polynomial is x minus 3 squared alone, what I'm trying to say is, if you think about being in a world so imagine, independent of other information, that you're given the Smith normal form of a matrix looks like blank, blank, x minus 3 squared. Right? Zeros elsewhere. How can you fill in those blanks if we're talking about a 4 by 4 matrix? Well, you could do it like in the example, right? You could have x minus 3 squared, which would correspond to being given something that has Jordan form like so, right? Or, what's the other possibility? Yeah, exactly. X minus 3 also satisfies the, divisibility conditions.
So would that be 1 Jordan block size 2, 2 Jordan blocks size 1?
Yeah. So that would be the origin story, if you will, of that Smith normal form. A matrix which has this Jordan form. What I'm starting to describe to you is that we can actually read the list of invariant divisors off the Jordan form if we have it. Or vice versa. If you have the list of invariant divisors, you can write down the Jordan form. So Jordan form, in some sense, is the matrix equivalent of the invariant divisor decomposition of the fx module. All right. So knowing the minimal polynomial does not fix the Jordan form, but it does constrain it. But knowing the Jordan form tells you the minimal polynomial. Perhaps not directly, but with some thinking. Yeah.
Can you have like 1, 1, x minus 3, x minus 3?
Not if it's a nope, because we need quartic, so that's why we can't do that. Yeah. Of course, if you're just talking about if you want to say fill in 3 blanks and you only have eigenvalue 3 to work with, that's a different game. You could also put an x minus 3 to the 4th down here, or an x minus 3 cubed, right? Then that would force you to put x minus 3 here. If you put a cube here, push 3 here, and then 1 there. But these basically are just the other side of the coin of describing what are the possible length of 3 chains. Like if I've got a length 4 generalized eigenvector chain for eigenvalue 3, then that's everything for R4. If I have a 3 chain, I still have one thing left. If I have 2 chain, well, I've got 2 things left. So I can either make one length 2 chain and another length 2 chain, or 1 2 chain and then 2 1 chains after that. So I'm going back to how we described the construction of the Jordan basis, which of course I never proved, but in a kind of sideways way, we have a proof of it here, right? Because the invariant decomposition of the fx module exists, which means that the elementary divisor description of the fx module exists, which means that the Jordan form exists, provided that the prime factors of the fx module are all linear. So it's always, still the case that we only have Jordan form technically if our eigenvalues are all found in the field over which we're working. All right. So this was good. And then I added this monstrosity, which I think if you can understand this one, then you're good to go. All right. If you can do this, you should probably be okay. Although I still made the grievous error at the start of this slide in the same period of calculation. In fact, after I did this, I made the error I underlined in green earlier in this. So it doesn't bode well for me. But who knows? Maybe I'll teach this course again, and then I'll get a chance to fix my thinking one more time. All right, so anyway, here's your xi minus a. So the first thing I do when I've got a Jordan block is I use the 1 to my advantage. Like if I've got a Jordan block somewhere, I'm going to take that 1, I'm going to put it in the upper corner through some row and column swippity swappity, flippity floppity. So there I put it up there. Then I subtracted x minus 3 times row 1 from row 2, which put that there. I used this 1 to clear out this, so that gives me this. And if you think about the ability to, if you've got a block diagonal matrix like this, if you have the ability to row and column swap, what that basically gives you license to do is to what?
Move blocks.
You move blocks around, exactly. So basically, I can take this, flip, and then flip, And then and I wanted to do that because I want that x minus 3 squared out of the way. So that's the first thing I did. And then I played the, let's see, what did I do next? I got a 6 minus x up here somehow. How did I do that? I don't remember how I did that. Somehow I did it. I've forgotten how I did that. How on earth did I do that? How did I get a 6 minus x there? Negative 2 times row 3 to row 2. Yeah. Yeah. I'm sorry. Well, there's some kind of typo here. But I'm sorry. I was thinking something but writing something else, I guess. But anyway, after you can make that happen there. Once you do get that expression there, that when you add this to that, gives us the 1 like I wanted. And then you subtract x minus 3 times row 2 from column 3, which puts an x minus 3 like this down here. That simplifies to x minus 3 times x minus 5. Anyway, after like 3 pages of this, and it starts to get like the greatest common divisoring, so to speak, or I could say the bazooing. It gets more sneaky, like this one. Well, obviously, x minus 3 squared plus that is 1, right? So, yeah. So, how'd that help us out? Well, like I'm going this, x minus 4. Then I've got x minus, oh, you know what I did was I brought the x minus 3 squared back up. Brought it back into the game. Back up here, back into the game. And then, so I've got this x minus 4 down here. To bring myself a 2 minus x times x minus 4, I just need to take like 2 minus x times this row and add it to that row, right? Then that will give me a 2 minus x times x minus 4 right there. I've already got my x minus 3 squared after my flippity floppity. And so then what happened? I'm not sure what I'm... Oh, okay, then I added the, okay, so here's steps. I added that row to there, right? Then I've got this. I'm almost ready to be, multiply column 1, 2, 3, 4, column 5. Hey! 5, column, these is, I can't count. Column 4 plus 2 minus x times column 5, guys, all right? So beware my inability to count, all right? Despite this non-trivial number of errors in this calculation, I think it may still be useful to you to see the idea of what we're doing, yeah? So I left it. Because, of course, I was aware of all these these errors when I scanned it yesterday. I don't own whiteout. But anyway, yeah, so when you add that to that, you get the 1, which was premeditated, yeah? Because basically the point is, when you look at this and that, you ask yourself, let's see, you look at this, you look at this and this, all right? I put this guy down in there for later. So when you look at x minus 4 and x minus 3 squared, what's the greatest common divisor of that? Well, it's pretty clearly, those are relatively prime, right? So those are going to give you a 1 if you put them up where they should be. All right, so next, I fixed that block. All right, now we're finally down to the final two of x minus 4 and x minus 3 squared, and this triple product, like so. And then this is some arithmetic to work out that after you do the appropriate row and column operations, you end up with x minus 4 times x minus 3 squared there. And so, great. And then, well, it's actually somewhat obvious that the greatest common divisor of this and that is what? X minus 3 times x minus 4, right? That's kind of obvious. What I think is less obvious is that clearly minus 1/2 x minus 3 times x minus 4 times x minus 5 plus 1/2 of x minus 4 times x minus 3 squared is clearly x minus 3 times x minus 4, right? I mean, obviously, you have this linear combination of that and that gives you that. So here's how to get the greatest common. You think it is clear? Oh, okay, good. Yes. We could use the division algorithm. Fine, you know things, curses. So maybe more magical. But since you remember things, it's not magical. You're right. It's just the division algorithm of polynomials. Fair enough. Okay, so with that in mind, the path is clear. I need to use this linear combination to, change this into a not a 1, but into an x minus 3 times x minus 4. So that's done. I just look at the blocks which are relevant. And long story short, there you go. That's Jordan form here. X minus 3 times x minus 4, x minus 3 squared times x minus 4 times x minus 5. Without scrolling back, let's see if we can write down the Jordan form. Given that, can you guys write down the Jordan form? You still remember? Unmember it. I've forgotten it, so it still works for me. So the minimal polynomial of A is what? X minus 3 squared. All right. The characteristic polynomial of A is what? Characteristic.
Do you combine everything?
So you want to start with the 5?
Or, I don't know,
Start with the what? The 3?
start with
All right. So we have 3, 3, 3. The question then is, what kind of blocks, right?
We also have a 2 block, right?
Right. So that puts that there. And that's it. Yeah, because that now we have algebraic multiplicity 3 from these blocks. And then that means that we've got 4 and 4 because we don't have a, we just have, there's no Jordan block for eigenvalue 4. They're just 4s. And likewise, well, there's just one 5 to work with anyway. So it forces us to write that, yeah. Which is, of course, what we started with, yeah. Which, since you guys made the eigenvalues go in order, is exactly what we started with. But you see that there's a choice of, I mean, the Jordan blocks can be reordered, right? There's no divisibility there. Just like the set of invariant, the set of elementary divisors have no sort of divisibility conditions, right? So elementary divisors can be put in any kind of list. Correspondingly, the Jordan blocks can be put in any kind of order. Like, I don't even have to arrange all the 3s together or all the 4s together. I'd still have a Jordan form, you know? I mean, it's just common human decency to put them in order, but, you know, it's, and some books probably would demand it to maintain some semblance of uniqueness, but
use the total ordering of the field that we're given.
so, all right. Let me put this away here. Oh, well, actually, was there anything else in here you guys want to talk about? Do you understand what the rational canonical form is, or no?
You could explain it real quick.
Explain it? Okay. Let's see here. So, this matrix, for example, this one here, let's see here, the characteristic polynomial I've written there, right? The minimal polynomial is what? It's just the same, oh, it's the same thing. This is like my 2 plus or minus 3i example. This actually is a non-derogatory in the sense that the minimal polynomial is the characteristic polynomial, I believe. In most books, the rational canonical form for this is exactly that. So the rational canonical form goes back to a basic lemma, if you will. Let me turn on the lights here and do that for a minute. It's all about the existence of these t-cyclic bases. So, you know, if you have t going from v to v, you know, finite dimensional, then we can build the, let's say, I'll put v naught. I'll just put v, how about that? I really want to put x. I mustn't do it. So this is, you know, by definition, so this is where that would have hurt me, f of x v such that f of x is in, you know, polynomial, right? So what is that? Well, that's f of t v such that, you know, but the thing is, this is an ideal of the endomorphism. Excuse me, it's an ideal of VT. This is a submodule, actually. And that's a, so we can, there's got to be an order for it, right? I mean, the point is that this can also be, good grief, I'm losing my words here. The point is that there exists some polynomial, you know, let's say C0 plus C1x, ckx to the k, in fx. Oops, we want it to be monic. So there exists some monic polynomial of some degree, k. Here, of course, k is less than or equal to n, such that what? Such that c0 plus c1t plus da-da-da plus t to the k, when it acts on v, it equals to 0. And there has to exist a monic polynomial of least degree which that works for. If you just think about it, if you think of all the set of polynomials which annihilate v in this sense, monic polynomials which annihilate v in this sense, by the well-ordering principle, there has to be a smallest element in that set, smallest degree. And so that, if you really think about what I'm doing, you'd recognize this is the argument for the division algorithm over polynomials. And that's why when you look at books that prove what I'm doing right now carefully, they just use the division algorithm on the fx module to prove what I'm saying. Namely that there exists this polynomial and no lower, there's no lower, like this is the smallest, in some sense, the smallest linear dependence that gives us back 0. So what that means then, what that implies is that v, tv, t squared v, t to the k minus 1 v, this is linearly independent spanning set for vv, for Langle v, wrangle. And so this is the so-called t-cyclic basis for this submodule. You can always find these t-cyclic bases because if you pick a non-zero vector and you just go to town on it, it can't go on forever. It's going to generate one of these submodules, right? And with respect to this kind of submodule, with respect to this basis, what is the matrix? And so, by the way, if we think about T of this subspace, well, it's a submodule. It's, in fact, an invariant subspace, right? So if I call this thing, say, beta, I can talk about T, horrible, but this thing, right, which would be a block. So if you take that basis beta and you extend it past the submodule, you'd have a basis for the entire vector space. But with respect to this particular part of the basis, you'd have a block diagonal piece of the matrix, the whole matrix for T. If you keep, if you make a whole, the entire basis for the vector space in this fashion, you string together a bunch of T-cyclic bases. Each one is T invariant, so it's going to give you a block diagonal matrix, and each one of those blocks is going to look like what I'm about to write. All right, so what's the definition of this? Well, we take T of V, beta coordinates, right? T of V, T of TV, yeah? Beta coordinates, and so forth and so on. Eventually we get to T of T to the K minus 1 V, right? Beta coordinates of that. And so what you're looking at here is 0, 1, zeros, 0, 0, 1, zeros. The next to last column, 1 in the lower thing. And then in the last one, this is, of course, T to the K acting on V, which you can take this up here and you can solve TK acting on V is minus C0 minus T1V minus, there's C1 here, but C, minus C to the K minus 1, T to the K minus 1 V, which then gives me minus C0 minus C1 minus CK minus 1. This block matrix I just wrote is the companion matrix. It's the companion matrix for this polynomial right here. Call that thing G of X. This I just wrote in the corner is the so-called companion matrix of G of X. It's a K by K matrix which is representing that polynomial, really. And so that's what you see over here. This is the companion matrix. This is the companion matrix of the characteristic polynomial. And so each one of the Jordan blocks, if you want to think about it, well, again, the Jordan form has, the rational canonical form, I think, is, well, how to say this? Which one is, you guys help me out here. Here's another one. This 5 by 5 matrix has characteristic polynomial. Another fifth order characteristic. Curses. Well, I guess it's okay. The larger point is, you can find, you can actually find a, let's see here, how would I say it? There is a t-cyclic basis for this piece, and for that piece separately. If you have an eigenvector, it's already, if you think about this, what if I have an eigenvector? Is that a basis? It's a basis in and of itself, right? Because t of the vector gives you lambda times the vector. So you can't, if you look at v and then tv, you've already got linearly dependent. So when you look at this kind of t-cyclic basis, if you're using an eigenvector, it stops at 1. And that corresponds to these 1 by 1 blocks. Whereas this, how to say this? Well, annoyingly, the other thing that's clouding the issue here is the distinction between real and complex. But, well. Right. So, not that you guys care, but Curtis linear algebra has clouded my understanding of things because he has arranged the rational canonical form by a strange choice of t-cyclic basis. He has so chosen the basis not as exactly a t-cyclic basis, sort of a modified one, in such a way that his rational canonical form becomes the Jordan form when it's possible, because he arranges to have like ones in the super diagonal, and when the blocks all become 1 by 1 blocks, well, the ones in the super diagonals are there, but you just have the I surviving, so you end up with like, anyway. You guys don't care about Curtis. I don't know why I'm talking about it.
So
Sorry.
when we go from the Smith normal form to the rational canonical form, we can take the invariant factors that we find and then basically write their companion matrix as block diagonals across the rational canonical form.
Right. I think that's it. Yeah, that's the example I'm missing. It's in my book. That's a good question, though. How do we go from Smith normal? Because I described how to go from Smith normal to Jordan form. But we're also interested in the question, how do you go from Smith normal to the rational canonical form? Good question. So you said, all right, let's try it. So you said, if we had something like 1, 1, x minus 3, and let's suppose we had x minus 3 squared, x minus 4 squared. What would that tell you? What are you thinking? What would you forecast the rational canonical form would be for this one? There now at least makes sense. idiot.
I would probably multiply the x minus 3 squared and x minus 4 squared.
Yeah, I'll expand it. Yeah, it's you have one down to the side.
Oh, okay.
Across the right.
Right, so if one of your invariant factors is just x, then we have, then the block is just 0.
Oh, really?
I think so, yeah.
Guess that makes sense.
I think that's what I found on the
I should be able to figure at least that much out, but so that's what you think, huh? All right, well, I'll try to think some more about this. We can talk about that next time. But what I wanted to talk about today also was a little bit just about the larger question of like the Wedder. I wanted to at least discuss with you guys what Wedderburn's theorem is, the Jacobson radical is. I don't really plan on doing much with that for you guys, but I just want you to be aware of the terms and what they mean. It's kind of neat. Whether it basically comes down to the question of like, what are the possible algebras? What do they look like? Well, with certain technical conditions put on it, I can answer that question. If you just say, what are all possible associative algebras? That's too hard. There's a lot out there. Thanks, guys.